My name is Harald Dillersberger, as Bernd said, and I'm working for Matrix Industries, which is a startup company in California. But my office is here at TU Graz. I'm a PhD student. Before I worked for 15 years for AMS and NXP as analog design engineer. So I started this work on thermoelectric energy harvesting next to my job at NXP some years ago, and then started the PhD where I made a test chip, and then I could find a company which is interested, which is Matrix, and then we designed 2 product chips, and I will talk about these developments today. And yeah, what is thermoelectric? An autonomous system which is powered by thermoelectricity. So first of all, a thermoelectric generator is just a Peltier element. So I hope you can see it here, the white one. This is just a normal element which consists of more than 100 thermocouples. And when you have a temperature difference on this one, which I can make here by body heat, and the temperature difference is to the heatsink, which has the room temperature. Then hopefully, I don't know if you can see this. I think not. Can you see the LEDs?
Yes, yes, that's it.
Okay, but I think it's too fast for the camera perhaps, so I can't see it. So this is moving. There are LEDs blinking, and this is just powered by body heat. Normally in my lecture I put it then to the window, which has which is colder than the room temperature. Then the LEDs go into the other direction. So this is how the circuit is built. I will show it later on. But let's start with the introduction and motivation. So I guess you heard about the Internet of Things. So this is a network of smart devices, sensors, typically wireless sensors, which are often remotely located. So they monitor and control really everything. And of course, they also need power. So the number of connected devices is growing, and the biggest, so the largest number are Internet of Things, so the PCs are constant, smartphones are growing slowly, and Internet of Things is growing fast. Here we look at the wearable devices. So these are also devices which are not connected to the internet. So for example, fitness trackers, also they are growing fast. And all these devices need to be powered in future. So here we have an overview which devices this could be. This starts from head over ears, eyes, body, down to the shoes. Also, there are smart shoes which can be powered by piezo elements. But many or some of the devices can use body heat. So we come to the power challenges. So batteries are large, then the replacement is problematic, and also recharging. So when the device is not accessible, this can be the main problem. But of course, also energy harvesting has problems, so that the power is limited. So typically it's not very high, and additionally it needs complex power conversion and energy storage. And also the power management consumes energy. And I think this is clear. The load is limited to the harvested energy. So we cannot consume more power than which is produced. But of course, over time, it can be duty cycled. So a battery or capacitor can store energy over hours for example, one transmission of a sensor. This is possible, but the sum of consumption cannot be higher than I think this is clear. So when we look to the use case limitations for thermoelectric, of course, it requires a temperature gradient. Photovoltaic needs light and piezo motion or force. And it's very difficult to avoid interruptions. So yeah, the sun is not shining for 24 hours. So you always need some kind of storage for the energy, and usually it's limited to the secondary power, so you have another power source. But the future is optimistic, hopefully. So electronics is consuming less and less power, and the harvesters are getting better and the power management more efficient. So there are more and more opportunities for energy independent IoT devices. So here we can see the power consumption of microcontrollers goes down, for example, and the energy of the energy harvesters goes up. So when we look at the thermoelectric generator, the efficiency is improved over the years, but still there is very low voltage. So the output is as low as 20 millivolts. It's possible to use more thermocouples, but then the impedance is increased. So at same voltage, this gives lower power. So there are also limitations. But the electronics, which is powered then from the thermoelectric generator, needs a voltage of more than 1 volt, or at least 1 volt. So there is a need for an ultra low voltage and high gain DC-DC converter, and additionally, there should be a perfect impedance matching. So the equivalent circuit of the DG is a voltage source where the open source voltage VOC is linear. So is a multiplication of the temperature difference by a constant factor, and the output resistance is a resistance which is constant. So this is the RDG here. This is, for example, 12 ohms. Then also the input of the power management circuit should have exactly 12 ohms to have a perfect impedance matching. So this is also very important for this circuit. So look at the existing solutions. There is the LTC 3108 from LinearTech, which is now Analog Devices. So this can start and operate below or at 20 millivolts. So it's using a Meissner oscillator here. So a CMOS Meissner oscillator with a depletion or native device. So these oscillations start already at few millivolts. Then it has a limiter and a rectifier or a voltage doubler. So this is very good at very low voltages, but at higher or already medium voltage is like 100 millivolts, we will see later the efficiency already gets worse. And additionally, so the input impedance is depending just on the parasitics of these devices. So the frequency is depending. This gives by with the inductance of the primary winding of the transformer. This gives the input impedance, and this is depending on the components, and additionally it's not constant. So there is a bad impedance matching except of one point which can be adjusted. When we look at the normal boost converter, so just an inductor based, so one inductor, an NMOS and PMOS, then of course this needs more than a threshold to work, which is normally then around 600, 700 millivolts. But they use additionally, so here this is called cold start, they use an internal charge pump, which is already working at 330 millivolts, which is good, but for many applications this is too high. So especially with body powered applications, the input voltage is normally below 100 millivolts. But of course, at higher input voltage, the efficiency is very good. Then this solution, so it's a transformer reuse boost converter. This is from a paper. So use a transformer-based oscillator like LTC for startup and low input voltage, and at higher input voltage, they reuse the secondary winding of the transformer or a normal inductor-based boost converter. And yeah, the problem here is that in between, they have the lowest efficiency at around 100 millivolt, and this is a very interesting operating point. So yeah, this is also a big disadvantage. So yeah, now I come to the novel flyback DC-DC converter. So this is my development. First, when we look at the normal inductor-based boost converter, when we go from 20 millivolts on the input to 4 volts on the output, we need a duty cycle of 99.5%. This means that the NMOS is on for 99.5% of the time, and the current in L1 is increasing very slowly, and the other 0.5%, the PMOS is on, and the current is going down to zero again very fast. So this is, first of all, very hard to implement because the switching times are very short, and this has a very bad efficiency. And when we look on the flyback, then we use the transformer. And for example, so here we have 1 to N. When we use a 1 to 50 transformer, then the current on the secondary side is only 2% of the current on the primary. So the current is ramping up again slowly, but also ramping down slowly by a factor of 50. And so the D1 on time is n times longer. So we just need a duty cycle of 75% from 20 millivolts to 4 volts. And this is much easier to implement and has a much better efficient. There is an additional advantage. So when we look inductor-based converter with a constant L1 and frequency, then the duty cycle for constant R in is a function of V in and V out. But when we look at the flyback converter in discontinuous current mode, so when the current goes to zero again in the secondary, then we can look at the average current, so the max, the maximum current is input voltage times on time of the switch divided by L1, so the primary inductance. The average current is then over a whole period, gives this one, and what we see that the final value is not depending on the input voltage and also not on the output voltage. So here last year when we were here in this classroom, I wanted the students to calculate the input resistance of the normal boost converter and calculate the difference between flyback and boost, but yeah, no one could make it. I think not even the professor could make it. Yeah, but this is not so important. So in the normal boost, also when the current goes to the output, the current goes through the input. So there is additional current and the input resistance is lower than in the case of the flyback. Okay, yeah, but the flyback has, of course, is not self-starting and cannot start with low voltage. So we also need a startup. Here again, I use the CMOS-based Meissner oscillator with a native NMOS and the rectifier diode. So this is just a one-way rectification. This is different to the LTC where it was ground-based. So this is the common voltage here is the positive voltage. And in C2, there is a higher voltage generated and the ground voltage is below the potential, the negative potential of the input voltage. So this voltage can then be used to turn off this start circuit because the voltage is lower and we have a negative gate source voltage on Q1 and it is turned off. So this can be done here by Q3. But here, as already said, this circuit has not a good efficiency. It's only used for startup, and afterwards the flyback converter is used. So this now we can see here the combination. So when we look back to the flyback, I just move this diode down here, which is of course no problem. So it's still the same circuit. So now I have here the startup with the rectifier over D1 and C2. And when the controller has enough voltage, so there is an internal voltage vector, then the startup is turned off by Q3. And with Q2, the flyback, which has the primary over L1 and Q2, and the secondary over L2, C2, and D1 can work. Additionally, there is the problem that to close Q2, so the switch, a higher voltage is needed than the supply voltage, and this is done by this simple boost circuit. So the voltage in C3 first is the voltage difference between input and ground is stored, and when the output switch is high, this voltage goes above the gate voltage. Okay, so here is a comparison of the novel circuit with the ones I showed before. Yes, so low voltage startup is not available for the boost. Right. So this also has no good low voltage efficiency. Mid voltage efficiency is not possible with any of the existing circuits, so this is very good here. Higher voltage efficiency is bad for the LTC. Also, there is no impedance matching. Then additionally, so the normal boost converters, they need an MPPT measurement. So they measure the open circuit voltage and then regulate the input voltage to half of it to have an impedance matching. This is also not necessary here. So here just the frequency and the on time are adjusted. So this saves additional power for the measurement. Then also no limiter is needed. Also no negative voltage on chip needs to be generated. This is also necessary here to turn off the startup circuit. And there are just few external components, but this is true for all circuits. This was, so the Mercury chip was then the first product chip which was done from Matrix, but it was designed at Certic Medical. This is where this is standing here. So this is our design house, but all inputs came from me. So everything is on chip. Low voltage startup, high voltage boost, output regulation, voltage monitoring, or ultra low power. And you just need input cap, transformer, and output cap. The Schottky is not really necessary because there is also an internal diode, but the efficiency is better with the external Schottky. This is the block diagram. So here is everything we saw before. Additionally, we have an 8-bit ADC, which is measuring the VOC. So there the Freiberg converter is stopping from time to time, and the open circuit voltage is measured and transmitted over 2 lines. There is also an PMOS which disconnects the output when no input power is available. So there is really just some nanoamps of leakage without input power. Yes, and perhaps this. Also, there is a synchronous rectifier. So in parallel to the Schottky diode, there is a high voltage DMOS. So 50 volt DMOS. This is necessary because on the secondary of the transformer, there can be a high voltage with the 1 to 50 or 1 to 100 transformers. Yes, so this is the layout, 1.2 times 1 millimeter, and the package, the 3 times 3 millimeter 10-pin DFN package. To the results. So, yeah, the DGs are improved and the power management is improved. So we have a startup of 24 millivolts for 12 ohms. So this is really the open circuit voltage. So the input voltage then is only 12 millivolts. The efficiency is up to 80%, or in some cases 85%. And this is, yeah, it says 250%, then competition. Yeah, this depends.